Okay.
Okay. Hi everyone. Welcome to another week, another Flan talk. This week. Oh, let me just check my sheet, my notes. Okay. Yeah, this week we'll have Wenyue presenting InductionBench. So LLMs fail in the simplest complexity classes. A paper. Yeah, I was very interested to hear about. So the stage is yours.
Thank you. Thank you for Anna and Andy for the invitation. So basically start my presentation. Okay, can you all see the screen? Okay.
Yep.
So hello everyone. I am Wenyue. I'm currently a postdoc researcher at UC Santa Barbara. So today I'm going to talk about InductionBench, which is a new benchmark that I managed to evaluate the inductive reasoning ability of language models. And basically what I noticed is that inductive reasoning is actually very hard for those language models, even for the SOTA language models, SOTA closed source language models. So although like we all know, okay, those language models they're saying, okay, they excel in mathematics or coding, but even in very simple inductive reasoning test cases, they fell pretty hard. So this is going to be today's roadmap. So I will give a very short background for language model and current LM evaluation, and then talk about InductionBench. And yeah, so so I think everybody is super familiar with large language models. So they're basically like huge transformer pre-trained on billions of tokens scraping from either a website or various sources PDFs. And those language models are becoming superior in various natural language processing tasks and also like reasoning tasks, question answering, sentiment analysis, mathematics, etc. And now there are so many different evaluation benchmarks in language models, hundreds of thousands of them. In general, they can be like divided into 5 different types. So knowledge and capability, which includes evaluating the knowledge, evaluating the reasoning ability, and then we have alignment evaluation for safety, bias, etc. And then for safety, including like risks, robustness, and then we also have like domain-specific evaluations in like, say, finance, legislation, etc. And so today we're basically talking about InductionBench, which is a benchmark that evaluates the inductive reasoning ability. So it naturally falls into the category of knowledge and capability. So let's first go over some like relatively well-known benchmarks in this area. So we have, of course, like a big chunk of them is about mathematic benchmarks, including like GSM 8K Math, Frontier Math Bench, basically various types of mathematical questions from primary school level to a graduate school level. And then we have coding, and then there are also like many almost pure logical reasoning benchmarks, such as like Dival, Folio, Logic QA, Context Hub, use propositional logic, first order logic, and having some either having some like contextualized scenario based on those logical rules to construct some like logical puzzles to solve. And then another big chunk of it is like common sense reasoning, which not only requires logical reasoning, but also requires some like common sense level of knowledge to solve this problem. So this 4 are what I think the most common types of like knowledge plus reasoning type of benchmarks. So in terms of reasoning, there are in general like 2 types of reasoning. So one is deductive reasoning and the other is inductive reasoning. So for deductive reasoning, the general idea is that, okay, we have a bunch of premises. For example, like all birds can fly. And then we have some observation. And then basically we are using those premises to try to deduce an answer based on the observation. Say if the observation is that, okay, penguin are birds, then the conclusion is that, okay, penguins can fly. So that's basically deductive reasoning, where we have a set of known premises, and we're just applying those premises, or say like rules on observations, and then to get a final result. And then inductive reasoning is kind of the reverse. So we don't have, say, a known or well-established rule or premise. And what we are trying to do is that, okay, given the observation, can we do some analysis to find out what are the rules, what are the transformation on those observations, and then get a conclusion about basically about what those premises are, what the rules are that can kind of explain this observation. So based on this categorization, we can basically see that most of the benchmarks that I just mentioned are deductive. So for math benchmarks, they are like very obviously like deductive. So basically the process of solving those math benchmarks is that first we translate those natural language description of like math questions into mathematic terms, and then apply very common mathematical operations to find the answer, to those questions. And then for coding, it's mostly like, we translate the question into the code syntax, like writing an algorithm, and then rely on the execution environment to deduce the final result. And for logical reasoning benchmarks, that's like very like clearly deductive, because they are basically relying on those deductive logical systems, first order logic, propositional logic, and the only thing that we require the language model to do is to directly apply relevant logical rules to deduce the answer. And then for common sense reasoning, it's kind of similar, other than that we need those models to recall some relevant common sense knowledge implicitly, and then kind of connecting those common sense knowledge plus the logical reasoning part to deduce the final answer. So basically, all of them are mainly deductive, and of course they also in some benchmarks they require some like domain specific knowledge in order to do this deductive reasoning. But in general, all of them are deductive. So basically, we're based on the landscape of benchmark that I noticed, currently in the LLM community, we are missing a lot of inductive reasoning evaluation benchmarks. So what is inductive reasoning? So some common inductive reasoning paradigms, so like data analysis. So given raw data, can we find features or insights from the data that can explain the observation from the data? And also like scientific discovery process is also like an inductive reasoning. We collect data, which is our observation, and then we are trying to do some pattern recognition to identify the trends, and then propose some hypothesis. And based on our hypothesis, we propose some experiments, and then again, collecting data from the experiments to do kind of another round of like, say, pattern recognition hypothesis experiments. And then finally, we got some theory or like rules that can explain what's actually going on. So I know AI for science now is like a very heated up area now. People are trying to say, okay, can language model discover some new proteins, or say, can language model help us to analyze some, say, physics data? But actually, the core process of scientific discovery, which is inductive reasoning, is very much missed from the current research landscape. So there are indeed some inductive reasoning benchmarks. It's hard for me to classify them into different groups because there are so few of them. So it's hard to do hard to do like a categorization. So some examples, for example, like this abstract causal reasoning. So basically, this benchmark is trying to evaluate the causal inductive ability. So given a bunch of like input-output pairs, we are requiring the language model to identify a set of objects that can trigger a special action here. And here, like the action is having a music. And basically we're asking, okay, can language model find the objects that trigger this playing music action? And Miniscan, another one. So basically, it's trying to ask the model, okay, can you uncover the grammar that map the input symbols, like those meaningless input symbols, to the corresponding corresponding images or sequence of images. And then list functions. So basically we also have input output pairs of list. And then can the model find out the function or some code that can generate the output from a given input. And then and then this mini ARC. Yeah, oops. Mini ARC. Basically, from those image, we also want to find out, okay, what's the rule that's behind those image transformation. And then we also have instruction induction. So given the demonstrations, can we find the natural language instruction behind those demonstrations? So basically, there are not so many inductive reasoning benchmarks, and there are also many issues related to those few inductive data set we have. So those current benchmarks cannot provide us a well-defined search space. So then it makes it hard to analyze or understand how well the language model is actually doing in inductive reasoning. So for the benchmarks that I just show, we have we ask those language model, okay, what's the instruction behind some transformation, but they don't actually provide us what's the search space. So we don't really know how hard the question is. And if the language models excel on it or the language model fail on it, can we actually tell anything about the ability of the language model other than that, okay, it can solve this specific question? And also, it's also missing a big part of inductive reasoning because, so Occam's razor is a pretty famous principle in inductive reasoning. So it's basically saying that, okay, there can be infinitely many different explanations or hypotheses under a set of observation we have. But what Occam's razor is saying is that can you find the simplest or shortest description among all those possible hypotheses? So this principle is kind of one of the foundational principles of inductive reasoning. But those current benchmarks, because they don't even have a good search space for hypothesis generation, we can't really say, okay, whether the hypothesis generated follow Occam's razor or not. So we don't really know whether the language model can find the shortest description, the simplest, nicest hypothesis behind the observation. And this Occam's razor is also kind of a by default principle to follow in AI for science. And of course, another issue related to the issue of no search space defined is that we can hardly scale up those benchmarks. We can hardly kind of increase the difficulty level of those benchmarks. So for example, if we train a language model in one specific benchmark, okay, it can solve it, but then we still need a huge human labor to figure out another benchmark, another more difficult benchmark to test those language models. So because there's no, say, well-defined search space, we cannot easily scale up the search space to make the benchmark a bit harder for those language models, and then making it difficult to kind of establish the performance frontiers. So, so seeing all those issues, our goal in InductionBench is, okay, basically we're trying to propose a benchmark without all these issues. So first of all, we are building this benchmark on a pretty well-studied area of inductive reasoning theory, where we know very clearly what the search space is. And we also know very clearly whether a shortest description that follows Occam's razor can be found given some set of observations, some set of data points. And so all data points in our benchmark, there exists a known unique simplest function that can be learned from some given data set. Oops. And also, we can easily scale up the complexity. So we can easily scale up the search space to make the data point a bit harder to test those language models. So one day, if our language model is like is strong enough to solve current data points in the benchmark, then we can easily scale up the search space to make it harder, and then we can find out kind of the upper bound of those language models. So, so what our benchmark actually looks like. So our benchmark is basically based on string-to-string mapping in inductive reasoning. So here's an example of like what a string-to-string mapping can be. So an input character, so here is an underlying transformation for string-to-string mapping. So an input character A will be transformed into a B if it comes after another B in the input. Otherwise, the output is the same as the input. So here, if the input string is like say A and B, then A or B, then the output string is like there's nothing we need to change. If input string has length 2, then there is some transformation that we need to do, say like we have to transform BA into BB in the output following those transformation. And same here, and kind of need to notice that, okay, under this transformation rule, if the input is BAA, we will change it into like BBA instead of like say BBB, because this transformation is kind of triggered only by the input. So we transform the first A into a B, but will not transform the second A into a B. So basically, this is an example of like string to string mapping based on a transformation. So basically from here we can see its relationship to inductive reasoning. So basically, given a set of input-output pairs, then the question is, okay, can you tell me the transformation behind those input-output pairs? And the reason that we choose input-output like those string-to-string input-output pairs, one is that it's actually a generalized version of many inductive reasoning. And so it's a little bit far away from real life situations or real life data points, but it is like one generalized version. And the second thing is that, okay, those string to string mapping is pretty well studied. At least some classes of them are pretty well studied. So we will be sure, okay, theoretically, a transformation can be learned from some given data sets. So given those input-output pairs, people or the language model can propose a bunch of different hypotheses. It can say, okay, hypothesis 1 can be, okay, input A outputs as B when it comes after the input B, or another hypothesis can be like it comes after an output B, or basically there were like many different hypotheses that can be proposed. But based on a given set of input-output pairs, we can eliminate most of the hypothesis. So here, like hypothesis 2 is wrong because of this data point. Hypothesis 3 is also wrong because of course because it doesn't need like 2 input characters in order to incur this transformation. Also, like hypothesis 4 is also wrong. So basically, in our data set, we will provide a sufficiently large data set so that almost all hypotheses can be eliminated by some data points in the data set, and basically only one shortest hypothesis will remain. So basically, when constructing our benchmark, we will make sure that there exists exactly one shortest description, or say shortest hypothesis, that can be drawn given our input-output pairs as the input to the language model. So okay, now what exactly our benchmark will look like. So our benchmark is based on, as I said, like string to string mapping. And so So like there is a pretty well-established hierarchy in those transformation, which is known as like Chomsky hierarchy. And here we are mainly focusing on like a regular transformation or like regular functions, which is from this hierarchy the simplest transformation. And within this regular functions in the Chomsky hierarchy, we also have another hierarchy that kind of divide those regular functions into even smaller classes, which is called like subregular hierarchy. So the most complex one is non-deterministic transformations, and then weakly deterministics, and we have like then left subsequential, right subsequential, and also below them we have some like some other classes of functions. So within this subregular hierarchy, we are mainly focusing on left upper strictly local, input strictly local, and right upper strictly local. So so basically they are at the bottom of this subregular hierarchy. So basically the three classes of functions that we the three classes of functions of string to string mapping that we will focus on in InductionBench is like the simplest transformation you can imagine. And the reason we choose them is that, okay, first it's actually very it's the reason we choose them, one is that they are simple. So basically we want to see whether the language model can tackle like the simplest transformation that we know. And the second thing is that those functions, those transformations are very well studied. So we know what their characteristic sample is. We know that there exists a unique shortest description. We know what data set we need to provide to any algorithm or like model in order to find out this shortest description. And we know the algorithm, we know the time complexity, data complexity, everything. So those three classes functions are very well studied, which can kind of serve as a good theoretical foundation for our benchmark. And so the relationship between these three classes that we generate data points from is like presented as presented like this. So basically these three classes are non-comparable to each other. They have some overlap, but basically they are non-comparable. And what this three class of function will look like, or say like what the transformation within those functions will look like. So input strictly local functions is basically saying that, okay, for any character in an input string, its output is determined by k minus one input characters to either to the left or to the right. So so basically we have some kind of hyperparameter k to kind of control the complexity of each single function within this function class. And then for left output strictly local k functions, so it's kind of similar, other than that, for every input character within input character in the input, its output will be determined by k minus one output characters to the left. And then for the right upper strictly local, so yeah, basically every the output of every input character in the input is determined by like k minus one output characters to the right. So yeah, basically they are Markovian functions, I would say. They're kind of short-sighted, and the k is controlling how short-sighted they are. So basically these three class of functions are very simple and straightforward. And basically the hyperparameters that can control the complexity is, of course, like the first, the context window k. So how many characters in the input or output that our model needs to pay attention to in order to determine the output of some characters. And second, the vocab size. And third, the quote unquote number of rules, which is basically how long the shortest description will be like in this transformation. And here for each transformation, I'm basically kind of distill it into a set of quote unquote like rules. So what so here one example is is that, okay, we have vocab ABC with k equals to 3 and the number of rows equals 2. So each rule will be like, okay, an input character A be transformed into a B, every counter comes after 1B. So this can be seen as like one rule. And the second rule in this whole like functional transformation is an input character B will be transformed into a C if the output is come after two consecutive C's in the input. So these two rules is the transformation of some like input strictly local function. So basically we are using the number of rules to kind of describe how long, or say like how complex this shortest description will look like. And here, basically, given this three parameters, context window, vocab size, number of rules, we basically know the search space. And ideally, this search space can tell us how difficult this question is to solve for any model or for humans. And basically, the good thing about these three classes of functions is that their learnability property is very well studied. So so basically, any function within these three classes can be learned by polynomial data in polynomial time. So for input strictly local functions, the characteristic sample is basically determined as the set of input up pairs where the input is any string with length smaller than k, and the output is, of course, like the corresponding output. So this is basically the characteristic sample, which means that given this characteristic sample, we know that the underlying function can be figured out. And then for output strictly local, the characteristic sample is kind of similar. So basically it's a set of input output pairs where the output is any string with length smaller than or equal to k, and then the corresponding input. So so here the characteristic sample is a bit simplified from their original definition. Yeah. And basically, what we know is that from this characteristic sample, there exists a unique shortest description that we can learn. And here I will present some experiment result. So before the actual result, so here is our evaluation metrics. So we have precision, recall, and compatibility. So compatibility is the most straightforward one. So basically, is that so compatibility is trying to see, okay, given the rules generated by the model that we are testing, if we apply those rules, can we generate the input data, which is a set of input output pairs. So basically, we're trying to see, okay, can the predicted hypothesis generate the observation? Oops. And then for precision and recall is these two are basically trying to evaluate whether the proposed hypothesis is the shortest hypothesis. So precision is, okay, how many of the predicted rules are correct relative to all rules the model generated, and then the recall is how many predicted rules are from the ground truth set of rules. And here we evaluate on so here is some partial evaluation result from the paper. So here we are using k equals to 4, vocab size 4, and number of rules 3. And then for sample size, it basically means how large is the sample, the characteristic sample we are providing to the model. So sample size 2 means that it's 2 times the smallest characteristic sample. So here, I'm basically testing on the SOTA models, open sourced or closed sourced. And in this setting, basically O1 mini and O3 mini are much better than other models. But they still fell pretty hard. So even for O3 mini, which is like one of the strongest closed source models we have. So even in this model, the compatibility is very low, only like 10%, 10%, 30%. So that's like a very low compatibility number. And for all other models, the compatibility is basically 0. So basically means that in this setting, we are already kind of reaching the upper bound of inductive reasoning ability in those language models. And then there are other results in the paper with even smaller, complex, even smaller K vocab size number of rows. And we can see kind of and with those even simpler classes functions within ISL, OSL, we will see a kind of non-zero result from open source models such as Llama and DeepSeek. And then basically we then test on like K equals to 4 and 5. And in these two cases, O1 and O3 are all like falling to 0 compatibility. So they cannot find we cannot find a correct hypothesis, let alone like the shortest hypothesis. And but still remember that those strictly local functions like ISL, OSL, they are at the bottom of subregular hierarchy, and regular functions is at the bottom of complexity hierarchy. And also like for now, the parameters are still like not very large parameters, I would say. And as a human baseline, so I asked 2 high school students that I know with 10 questions from like 10 questions from OSL, ISL, so 30 questions in total, and they're basically achieving like perfect scores. So basically those questions are very easy for humans. But our language model is failing. So this is kind of posing like a very straightforward contrast to many deductive, say, or math benchmarks where they're trying to, where many people are saying, or many papers are saying that, okay, those language models are already stronger than humans. They're solving like math questions that's so complicated that like maybe like normal, like non-math students cannot solve them. But in inductive reasoning, they are like much lower than, like they perform much lower than humans. And then some result about like parameters, some like parameter sensitivity result. So basically the impact of K, so increasing K can markedly reduce recall precision compatibility. And then for impact of vocab size, so what I noticed that when K or number of rows are relatively small, the vocab size doesn't really matter. And yeah, and then for the impact of R, so with so when the K or vocab size is small, so here K equals 2, vocab size equals 2, increasing the number of rows doesn't really hurt the performance. But when we have like larger K or larger vocab size, increasing the number of rows does kind of does impact the result a lot. And then some other experiments, for example, like I use like few short examples in the prompt, and it kind of helps in the case when K equals 2, but when K equals 3 or 4, it doesn't really make any difference. And another thing we notice is that if we increase the sample size, it actually hurts the performance. So this is different from say neural model, like neural network learning, where basically in neural network, the more data, the better. But here, if we increase the sample size in the context, then it actually hurts the performance a lot. So one reason we thought is that, okay, it could be the case that it's increasing the context length, and we all know that language models, long context still like a big issue for language model. So another experiments we do is that we are repeating the samples in the context. So say original like the characteristic sample contains 10 input output pairs, and we are repeating those 10 samples by 5 times, and then we are basically increasing the context length. But what we see is that like repeating those sample size, of course, it does hurt the performance as well, but it doesn't hurt that much. So it won't decrease the result to 0, at least when k equals 2 and 3. But if we actually put different samples into the context, it can decrease the performance to 0. So more data hurts the performance, and it is not just because it extends the context length. So yeah, so that's basically the experiments we have. So basically the summary, we are building a benchmark on inductive reasoning based on pretty well studied theories in inductive reasoning. And then what we noticed that those language models fail in almost the simplest classes, and their performance is much worse than humans. And then we also did like some experiment to see what parameters are impacting the performance of those language models. Yeah, so that's basically the paper.
Awesome. Thank you.
Okay.